Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to go through more details on how we are going to apply a parameterized policy to the continuous version of Mountain Car. It's good to go over what the differences are between discrete Mountain Car and continuous Mountain Car, since they are not obvious. Specifically, the reward structure for Mountain Car Continuous is different. You can also see this information on the wiki page at the URL shown here. So in Continuous Mountain Car, if you get to the goal point, then you automatically get a reward of 100. So unlike Discrete Mountain Car, your reward can be positive. However, subtracted from the 100 is the sum of squared actions you take. So if the magnitude of your actions is larger, each step you take is penalized more. So your agent should be incentivized to take smaller actions. The environment is considered solved if you can reach an average total reward of 90 over 100 consecutive episodes. Note that while the action space is continuous, your action must be between -1 and 1. Next thing is, while we could implement the policy gradient theory directly, we are instead going to take another approach. The problem with gradient descent or gradient ascent is that it doesn't seem to converge nicely in this scenario. What we'll do instead is a special type of random search called hill climbing. Hill climbing works as follows. Suppose we only have two parameters so that we can show the parameters on a 2D grid. First, we initialize the parameters randomly. This is the green dot. Then we play one episode or a few episodes with these parameters. Playing fewer episodes will increase the variance of our estimates, and playing more episodes will decrease the variance, yielding better estimates, but it will take longer. The reason we want to play a few estimates is to get an idea if these parameters are good or not. If the parameters are better than the best parameters we found so far, then we set these as the best parameters. Otherwise, we stick with the original. So next thing we do is we generate a new set of parameters by randomly perturbing the current best parameters. So basically, this new set of parameters will be in the neighborhood of the current best parameters. We then test these new parameters to see if they yield a good average return. If they are, then we set these to be the current best parameters, and so on. Eventually, we'll have tested many sets of parameters, sort of walking on a path up a hill, hence the term hill climbing. Note that the path is always going to go in an increasing direction of the average return. You may also recall from Deep Learning Part 2 that this was one of the methods we suggested could be used to find a good set of hyperparameters for training a neural network. So this is in fact just another optimization technique, not unique to reinforcement learning, but particularly helpful in some situations. I found that this method generally yields more consistent results than gradient descent, and it beats trying to do a hyperparameter search. However, since you have all the skills you need to build a parameterized policy and perform gradient ascent on the performance, you are encouraged to try and to see if you can find good hyperparameters. Try using both neural networks and linear models with radial basis function kernels.